seventh period, so most days I was
I had
just
it
like
six.
asleep.
I thought we used it. Oh, we guys have
Wait, were you guys in?
I'll just work it.
Like,
I was in six.
yeah, I was in six.
I had seventh. I was just done. It's a long day.
Seventh is a hard day for us.
Yeah.
Even sixth is hard now. I can't get through sixth period without losing my mind.
All right. So we're going to talk about linear systems, systems of differential equations. An example of where we might end up with a system of system of differential equations. So think of Newton's law of cooling. So the change in the temperature is proportional to the difference between the temperature and the ambient temperature. Okay, so now think of two aquariums that are next to each other, and they're insulated all around. So the temperature change in the temperature in one aquarium is the difference between its temperature and the temperature of the adjacent aquarium. Well, the adjacent aquarium, the change in the temperature there is the difference between its temperature and the other adjacent aquarium. So those two differential equations are kind of interlocked. We have a system of differential equations. So I think that's the most straightforward example of when we end up with a system of differential equations. So a linear system, the normal form of a linear system, and this is a first order system. We write dx1, oops, not d prime, dx1 dt equals a11 of x, x1 plus a12 of x, x2 plus dot 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 plus a1n of x, xn plus f1 of t. So this is a non-homogeneous differential equation. And then we have a second variable, dx2 dt is a21 of t, x1 plus a22. Sorry, and these should be t's, not of x's. Sorry. T x2 plus a2n of t, xn, plus some other function of t. And we have n of these. dx of n dt is an1 of tx1 and 2 of tx2 plus dot 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 plus a sub nn of t xn plus f sub n of t. And we usually just call this a linear system. And we're assuming that the a sub ij of t and f sub I of t are continuous on some common integral. And the system that I just described with Newton's law of cooling, we would have just two derivatives for the two tanks, and we'd have two terms here. If f sub I of t, those functions there at the end, are 0 for I equals 0, 1, 2 up to n, the system is homogeneous. Otherwise, it is non-homogeneous. Now, a lot of what we talk about today today is an exact analog of what we talked about for higher order differential equations. We're just applying it to systems. So what we generally do is represent this system in matrix form. So we're going to let capital X equal the matrix, and what a nice thing about as you go further in math, we get less picky about how we write things. So all matrices we just show with parentheses. So x1 of t, x2 of t to xn of t. X prime is the derivative of this. And that is just x1 prime to xn prime. I'm dropping the t notation here. And a of t is just the matrix of our coefficients. So that's a11 of t to a1n of t. And f of t is our matrix of our functions. So we can write kind of in larger form the derivative with respect to t of x1, x2 to xn equals a11 to a1n, an1, ann times x1, x2, xn plus f1 to fn. And in more compact form, we write x prime equals ax plus f. And I'm using capital letters here to denote matrices. For a homogeneous system, we have x prime just equals ax. And this implies this. All right, so as an example, just writing a system, if we had dx dt equals 4x minus 7y, where x and y are both functions of t, and dy dt is 5x. So system of differential equations. We can write x prime equals 4750 times x, where x prime is dx dt, dy dt as a matrix, column matrix, and x equals xy. And I need to work extra hard to make my matrices capitals, my variables smaller. If we had a three-variable system, dx dt equals x minus y, dy dt equals x plus 2z, and dz dt equals minus x plus z. we would write x prime equals, our coefficient matrix would be 1, negative 1, 0, 1, 0, 2, negative 1, 0, 1 times x. Where x now is our column matrix xyz. You'd get a 3-variable system, the example I gave before. We had 3 water tanks that are all share sides and insulated on the outside, and you're applying Newton's law of cooling to all of them. All right, and we can go the other way as well. If we have a system, we can rewrite that as, as a matrix. If we have our system written as matrices, we can go back to written as a series of equations. So if we had x prime equals 3, negative 7, 1, 1 times x plus t minus 4, 2t plus 1 times e to the 4t. We would write this as dx dt equals 3x minus 7y plus t minus 4 e to the 4t, and dy dt is x plus y from here plus 2t plus 1 e to the 4t. All right, we good with transition back and forth between system notation and matrix notation? And we kind of go back and forth quite a bit in this unit. We can also write a single differential equation as a system of differential equations. Sometimes it's advantageous to turn a higher order differential equation into a system of first order differential equations. And we'll talk about an example of that in a couple of days. So higher order equation as a system. So let's say we have y double prime plus 2y prime minus 2y equals 3t minus 9. So, I mean, we know we have a method for solving a differential equation like this. But we want to rewrite this. To do that, we're going to say y double prime equals minus 2y prime plus 2y plus 3t minus 9. Isolate the highest derivative. So we're going to let y equal x1. So y prime, we're going to say is x2, which equals x1 prime. Sorry, not x prime, x1. And y double prime is going to be x2 prime. So we get x2 prime equals 2x1 minus 2x2 plus 3t minus 9. And x1 prime equals x2. So this now is a system of first order differential equations. And we can write this x1 prime, x2 prime equals 0, 1, 2, negative 2 times x1, x2 plus 0, 3t minus 9. And this is also x prime equals ax plus f of t. So we've rewritten that second order differential equation as a system of first order differential equations. And in certain situations, this is going to be nicer, easier, give us a way to solve the differential equation if this particular kind of differential equation would be hard to solve otherwise. All right, questions there? All right, a solution. To a linear system is a set of n functions that satisfy each of the differential equations. I'm going to say DE, that make up the system on some common interval. So just as we'd expect, the solution is a set of equations that when we plug them into the original differential equations, it satisfies each of them simultaneously. And that's what we're interested in this chapter. How do we find those solutions? We can write x equals x1 of t, x2 of t, to x of n of t. We call this the solution vector. The solution vector is just a column matrix. Now we can think of the solution as a set of parametric equations. And those parametric equations produce some kind of curve in space. So we have, if we think of a three-variable system, we have x of t, y of t, and z of t. We can think of that as a set of parametric equations describing some curve in three-dimensional space. So I'm going to say for a two-variable system, just because it's easier to think about, x1 of t, x2 of t, set of parametric equations. And they give a curve that we call a trajectory. In the x1, x2 plane. That we call the phase plane. So if our system is x and y, we have x of t and y of t, and our plane is the xy plane, and we get the parametric equations for curves in the xy plane. And I put in our little folder for various calculators and plotters. I put a phase plane plotter, a Wolfram Alpha widget, because we'll look at the phase portraits that we call them. If we plot a number of trajectories in the plane, we get what we call a phase portrait, and it tells us something about the behavior of the solutions to the system of equations. Just like a single differential equation, we can find general solutions and a general solution is going to contain constants. And a particular solution which have no constants. And if we have initial conditions that we use to come up with our particular solution, we have an initial value problem. And we can solve for the constants. So just like with the differential equation we worked with before, we can find a general solution that has a bunch of constants in it. We can substitute an initial value in to solve for our constants, or if we have a non-homogeneous equation, we have a particular solution and a solution to the homogeneous equation that contains constants. So we have a sum of two solutions. So let's verify a solution. I'm going to say x prime equals 2, 2, 1, 3 x, and we want to verify that x equals 1, 1 e to the 4t is a solution. Well, I'm going to rewrite x as e to the 4t, e to the 4t. And we're going to do the multiplication. So 2, 2, 1, 3, that matrix times e to the 4t, e to the 4t. It's a reminder of how we do matrix multiplication. Multiply this plus that times that. Rows times columns. So this is going to be 2e to the 4t plus 2e to the 4t for the first row. And for the second row, we get 1e to the 4t plus 3e to the 4t, which is 4e to the 4t, 4e to the 4t, which equals x prime. So we've verified that our matrix times this gives us the derivative of this. All right. So under the conditions that we specified earlier, and I'm going to say our coefficient matrix A of t and our function matrix f of t contain continuous functions. On some interval containing a point that we're interested in. That's our initial condition, if we want to think about it that way. Given that those matrices contain continuous functions, a unique solution to the system exists. So all we need, the only condition we need for existence of a unique solution is that we have this matrix of continuous functions. For us, for what we're doing in this class, this coefficient matrix usually will just be constants. And f of t, the functions that make our system non-homogeneous, are continuous. And we're going to only use certain kinds of functions for our non-homogeneous systems that make them nicer to work with. Then a unique solution exists. So that's not a super high bar for the existence of a unique solution. The superposition principle applies to solutions to homogeneous equations. As we might expect. So that means if x1, x2, xn are solution vectors, these are matrices with our solutions, then C1, x1 plus C2, x2 plus dot dot dot, Cn, xn is also a solution. So sums of solutions are also solutions. We have the idea of linear independence. So these are linearly dependent. If for some constants C1, C2, Cn, not all 0, C1, x1 plus C2, x2 plus dot dot dot, Cn, xn equals 0. And this is the same as saying one of our solutions is some kind of scalar multiple, sum of scalar multiples of the other solutions. If they are not linearly dependent, they are linearly independent. Linearly independent. And that would mean if C1, x1 plus C2, x2 plus dot 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 plus Cn, xn equals 0. then all the constants are 0. And we have a nicer test for linear independence. So if we have if x1 is this matrix, x11 to xn1, x2 is x21 to xn2, and xn some other column matrix, xnn. If these are solutions to a system of homogeneous differential equations, on some interval, they are linearly independent if and only if the Wronskian of these things, that is the determinant x11, x21, xn1, up to x1n and down to xnn, does not equal 0 for all t in our interval. So we have the same criteria with the Wronskian. Now notice there are no derivatives here. The Wronskian is just made up of the entries in our solution vectors. If the Wronskian is not 0, those solutions are linearly independent. And just like we talked about for higher order differential equations, for every t in our interval, either the Wronskian is not 0 or the Wronskian is 0. So if the Wronskian is not 0 for some t in our interval, then the Wronskian is not 0 for every t in the interval. So if you get some particularly complicated Wronskian and you could show that it's not 0 for some value of t, that means it's not 0 for any of the values of t that we're interested in. All right, so we're finally ready to get to our big theorems. A set of n linearly independent solution vectors for a different system of differential equations is a fundamental set of solutions. So our goal when we're solving these systems of differential equations is to find n, if we have an n by n system, we want to find n linearly independent solution vectors. And under the assumptions that we have for A and F, a fundamental set of solutions exists. So if that matrix, coefficient matrix, and our function matrix contain continuous functions, then a fundamental set of solutions to our system of differential equations exists. So our job then is to find it. If we have a fundamental set of solutions, our general solution is x equals c1 x1 plus c2 x2 plus dot 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 cn xn. So our goal is to find n linearly independent solution vectors to find our general solution. All right, we're almost done. A particular solution. Y sub p is any solution vector free from arbitrary parameters that satisfies the differential equation. Constants for us, for what we're doing. Arbitrary constants, and I'm going to say that satisfy the system. The general solution is y equals y sub c plus y sub p, where x sub c is the general solution to the homogeneous system, and y sub p is a particular solution to the non-homogeneous solution. So just like before, we form our general solution by adding our complementary, this should be y sub c. So all of these theorems are exactly analogous to the theorems we had for higher order differential equations. All right, so now we have our theory. Monday we will start talking about how we solve these things. And we solve them using some interesting linear algebra techniques and making some assumptions like we did about the solutions to our higher order differential equations. Yeah, that was a lot of stuff. A lot of words, yeah. There we go. Yeah, we're on an assembly schedule, so it was tight.